7.4 Similarity in right triangles. The objective in this lesson is to find and use relationships in similar right triangles. So this is specifically for right triangles. And we are going to be discussing the altitude to the hypotenuse of a right triangle. And altitude goes from the vertex to perpendicular to the opposite side. All right, remember that definition? So we are going from the vertex to the hypotenuse. So we are going from the vertex that makes the right angle and taking that altitude to the hypotenuse. So let's look at our theorem here. It says the altitude to the hypotenuse of a right triangle, this is for right triangles only, divides the triangle into two triangles that are similar to the original triangle and they are similar to each other. So let's take a look at this. We have if triangle ABC is a right triangle, which it is. So we have our purple triangle here, and mine is in nice, neat color. So we have our big triangle here, ABCD, and it is a right triangle. And notice that we draw the altitude to the hypotenuse. Our altitude, let's draw that in a different color. Our altitude to the hypotenuse here goes from the vertex that is the right angle and comes over here to the hypotenuse. Now, I told you before in right triangles, you always want to know where your hypotenuse is. That's the first thing you do. You go, oh, right triangle. Directly opposite of that is your hypotenuse. So we draw the altitude, which goes from the vertex to perpendicular to the opposite side. So we have this original triangle right here, our purple one, and we draw this altitude. And then what happens is that this, and I'm going to erase all mine, pardon me, creates two more triangles. And you can see them right here. This triangle right here. And this triangle right here. Now, because they are made with the altitude, they are also right triangles. And one main note here is that for our original triangle and our blue triangle, angle A is shared. Now, if you look, we take this triangle here, our blue one, and we flip it over and rotate it, and there's our angle and our right angle. And our green triangle has a right angle, and notice that it shares angle B with the original big triangle. Okay, and look here, you can see you have to flip it over and rotate it so that it lays there. So now I'm going to erase here. Here's our shared angle A and this right angle. Here's our shared angle B and this right angle. And here is our original triangle with its right angle. Now, what do you notice between the purple triangle and the blue triangle? There are two congruent angles. Because all right angles are congruent, we can make our right angles congruent, and they have the shared angle A by the reflexive property. Look at our purple triangle and our green triangle. They have two congruent angles, our shared angle B and a right angle. And what this means is that these triangles are similar. So the purple triangle is similar to the blue triangle. And the purple triangle is similar to the green triangle by the angle-angle similarity postulate. So if purple is similar to blue and purple is similar to green, then transitive property, right? Blue and green are also similar to each other. So this is the basis for everything in this section. And if we look at our theorem here, we see there's all right angles are congruent, and our reflexive property of congruence that makes our shared angles congruent, and our angle-angle similarity postulate, which makes our triangles congruent, and then again, all right angles are congruent, and we use CPCTC here to make a shared side, because we don't actually have a transitive property. But if we look back up here, this is a shared side between this triangle and this triangle. I got the wrong one there. Sorry. CD. There we go. Right? Do you see how that is the altitude? So we have a shared side, and we can use our angle-angle postulate. So it makes all three of these triangles similar. Let's look at what we do with this. We want to say who is similar. How do we use this? What similarity statements can you write? Well, we just did it up above. This is the theorem. But let's look at how you take on a problem like this. Look at all of these triangles here. What's the first thing I'm going to tell you to do? That's right, separate them out and draw them. So the first thing I'm going to do is I'm going to say I've got this big purple triangle here. So I'm going to draw my big purple triangle. There's my right angle. And then I'm going to break it down and say, all right, let's call this triangle here the blue triangle. So I'm going to draw in my blue triangle, and it has the right angle that is WY here, right, from our altitude WY. And what angle is shared between these two? Angle Z. And then I'm going to break out my little green triangle over here. So here's my little green triangle, and it has a right angle from the altitude. And which angle is shared amongst these? It's angle X here up on the top. Pardon me. And then we know that our blue triangle and our green triangle also share our altitude here, WY. We don't know if we're going to use that, but we know that that's congruent. It's the same side. So if we want similar triangles, here's our purple triangle, XYZ. So I start here at X, Y, Z. And my blue triangle, how do I write similar to that? Well, I started at X and went to Y, so there's my right angle, and then I went to my marked Z angle. So I need to go blank angle to right angle to my 2 angle here. So that's Y, W, Z. And then for the green triangle, how do I match it up to the original purple triangle here? Well, which ones match here, the right angle and the green angle. So I need to make sure that my right angle, which is y, and my green angle, which is x, are in the same spot. So x has to come first, and then my right angle on my green one is w, so there's my right angle, there's my green angle, and then what's left over is y, and we can look at the same way here. Our shared angle here is z, our right angle is w, so you can see where the shared angles are and the right angles are all in the middle. So these can be a little bit complicated, but if you mark everything and work your way through, things will work out. So now it's your turn. Let's look at the next problem. Go ahead and pause the video and give the next problems a try. This problem required some good diagrams, good labeling, and some thought. We were asked to write a similarity statement relating the three triangles. Well, I had my big purple one to start with, and I've got my right angle here and my altitude to the hypotenuse. And then, so I just drew my big triangle, and my right angle is on the bottom. And so now I filled in my blue triangle. And I just drew a triangle knowing that the right angle has to go at the bottom, and my shared blue angle Q needs to go over here on the left, because there's that's where it is in my original triangle. So I made my shared angle Q on the left, and where's my right angle in the blue triangle? Well, that's S. So I put S at the bottom, and that leaves P to go on the right. And then I did the same thing with my green triangle. I just drew a triangle knowing that the right angle has to go on the bottom. And I know that my shared green angle has to go over on the right. So I know that the shared green angle is R. And where's my right angle? Well, in my green triangle, that's S. So that has to go on the bottom, which leaves P up here on the left. And you can kind of see how blue and green are going to slide together here, with SP being the shared side. Okay, so then I just took my original triangle and I decided to put my right angle in the middle. So I just named it QPR. Now, why do I put my right angle in the middle? Because then my blue angles, angle Q, it's on the left. My green angle, angle R, is on the right. So it kind of looks like my triangle here. So when I go to write a similarity statement to my blue one, I know that the right angle has to go in the middle, and my blue angle has to go on the left. So that's triangle QS, and P has to be the last angle I put in. And then that's similar to, and now on my green triangle, I know that my right angle has to go in the middle, and my green angle has to go on the right. So I know that S is in the middle and R is on the right. That means P has to start. So these do require a little more thought, a little more effort, and color is definitely your friend on these. In the second part, it says, from our similarity statement, write two different proportions using the ratio SR to SP. So I went and I looked, well, where do SR and SP come from? SR comes from the green triangle, and SP comes from the blue triangle. So I simply wrote two more ratios, I completed my proportion, my extended proportion here, just starting with sides from the green triangle. So I said, well, PS, that's the first one. So who's the first one in the blue? QS. And then first to third position in green, PR. So first to third position in green in blue, QP. Not too bad. A bit challenging, but I really believe you can get these. All right, let's Move on. This is something we talked about in 7.2, I think it was. Means. Remember when we did means and extremes? And I told you it was going to come up later? Well, here it is. Proportions in which the means are equal. Okay, so your means, those are your inside numbers, bottom left, top right, which your means are equal, happen a lot in geometry. These are called a geometric mean, and it looks like this. Notice how our means are equal. They are both the value x, and we have positive numbers a and b. And it's just a proportion where your means are equal. So if we want to find the geometric mean, we're asked to find the geometric mean of two numbers, 6 and 15. So I simply write a proportion, and I know that it looks like that. Because my means are equal, and then 6 and 15 are my extremes. Now when I cross multiply, what do I get? I get x squared equals 90. How do we get rid of an x squared? That's right, square root, both sides. Square and square root are opposite operations. Well, what do I do with the square root of 90? How do I get 3 square root 10? Well, hopefully in algebra, you learned about simplest radical form. And what simplest radical form is you factor out perfect squares. And what's a perfect square? 4 is a perfect square. 9, 16, 25, 36, 49, etc., etc., etc. You should know these up to at least 15, if not 20, is your best bet. Because what is the square root of 4? 2. Square root of 9, 3. Square root of 16, 4. And on and on. So to do this, I have the square root of 90. Are there any perfect squares that go into 90? We are going to factor 90. And you've done this before, like 1 times 90, 2 times 45, 3 times 30. None of those are perfect squares. You are looking strictly for perfect squares. Well, how do I make 90? 9, that's my first perfect square that'll go into 90, times 10. So the square root of 9 times the square root of 10 makes 90. Now, I check again. Does 10 have any perfect squares? No, 10 is not divisible by 4 or 9. So we're done. So what is the square root of 9? 3 times, and 10 is not perfect, so it can't get out of square root prison. To get out of square root prison, you have to be perfect. So the square root of 90 in simplest radical form is 3 square root 10. And what that means, it's your turn. Pause the video and do the next problem. This wasn't too bad. It asked us to find the geometric mean of 4 and 18. So I know when I'm doing geometric mean, I write my fraction bar equals fraction bar, just set up a proportion, and my means are the same number. They are equal. They are both x. And then I put in 4 and 18 in my extremes, cross multiply. X squared equals 72. Take the square root of both sides, so x equals the square root of 72. Now I have to put 72 in simplest radical form. So I factored 72. I got the square root of 9 times the square root of 8, because 9 is a perfect square that goes into 72. And then I checked 8. 8 is made up of a perfect square, so the square root of 4 times the square root of 2. There are no perfect squares in 2, so I'm looking at square root of 9 times the square root of 4 times the square root of 2. And square root of 9 is 3, square root of 4 is 2, square root of 2 is not a perfect square, stays in square root prison. 3 times 2 is 6. Square root 2 is simplest radical form. Don't worry, we'll practice more on this later. You're going to have to know how to do simplest radical form. Okay, moving on. How do we use this? We have our corollary to our original theorem here. What's a corollary? It's an extension of a special case. And we're going to go through these next two pretty quickly because I want to get to the formula, which is what's going to be most helpful. Corollary 1 says the length of the altitude to the hypotenuse is the geometric mean of, and this is going to give us our two values. So our altitude to the hypotenuse, the length of our altitude, is the geometric mean. So this is our means. The lengths of the segments of the hypotenuse. So this is our extremes. So if we look here, our altitude, and then look at our hypotenuse. We have segment 1 and segment 2. So this is altitude, altitude, and segment 1 and segment 2. See how that works? In our example here, our altitude is 4. There's altitude, altitude, and then our extremes. Look at it, breaks our hypotenuse into segments. Here's segment 1, segment 2. Segment 1, segment 2. All right, it's just a formula. Our next corollary, corollary 2, says the altitude to the hypotenuse separates the hypotenuse, okay, so that the length of each leg is the geometric mean. So here's our mean. Your legs. Your leg is a mean of, and here's our two values, the length of the hypotenuse and the length of the segment of the hypotenuse adjacent to the leg. So here's our extremes. Let's write that down below. Here's our extremes. The entire hypotenuse and the segment adjacent to the leg. So let's take a look here. Here's leg 1. And our altitude. Here's our entire hypotenuse. And here is segment 1 that is adjacent to leg 1. So what this says, this is leg 1, this is leg 1. Goes in our means position. Here is the entire hypotenuse, and here is segment 1. Here is leg 2, and here is segment 2. So notice here, this is leg 2, leg 2. Those are our means. And still, the entire hypotenuse is on top, but segment 2 is on the bottom. So we have two formulas here, one for each leg. So if we look at all of our formulas here, we have one that deals with the altitude and the hypotenuse, the segments of the hypotenuse. One that deals with the left leg and the hypotenuse, and one that deals with the right leg and the hypotenuse. And if we go to this page, all of it is summed up right here. I can't draw enough stars. We'll even put some down the side. This right here is how you should label every triangle you're dealing with. A is your altitude, H is your hypotenuse, L1 is leg 1, S1 is segment 1, L2 is leg 2, S2 is segment 2. And then look right here. Corollary 1. This deals with the altitude and the hypotenuse. Well, the hypotenuse segments. Corollary 2. This deals with leg 1 and the hypotenuse. And leg 2 and the hypotenuse. So all you have to do, make sure you label what you know, write your formula, and substitute in. Let's take a look here. Find the values of x and y. First thing I'm going to go do, that's right. Here's my altitude, right? Goes from the right angle to the hypotenuse. I'm going to call this leg 1. So this is segment 1. This is leg 2. So this is segment 2. That's not where I want that. I need that space. And this entire thing is the hypotenuse. So what am I going to do first? I'm going to use my leg formula first, because that's for x. So to find x, I'm going to use hypotenuse over leg 1. I'll write it out for you this time. Leg 1 equals leg 1, because that's the means, they're the geometric mean, over segment 1. So let's look here. What's the length of the hypotenuse? 12 plus 4. What is the length of leg 1? X. So they put the hypotenuse on the bottom here. What's the length of segment 1? 4. And here's my geometric mean. Square root of 64. 64 is a perfect square, so x equals 8. This leg is 8 units long. All right, how do I find y? Well, y is the altitude, so I need the altitude formula. I know that segment 1, we'll write it out, segment 1 compared to the altitude is my geometric mean compared to segment 2. So what's segment 1? 4. That's segment 1. Segment 2 is 12. And my geometric mean is the length of the altitude. Y squared equals 48. Oh no, how did they turn 48 into 4 square root 3? Well, square root of 48 Perfect squares. Start with 4. Does 4 go into 48? Why, yes. Yes, it does. 4 times 12. We have to check again. 12 have any perfect squares? Why, yes. Yes, it does. Square root of 4, square root of 3. 4 times 3 is 12. So that's square root of 4 times square root of 4 times square root of 3. 2 times 2 times square root of 3. Not perfect, can't get out of prison. 2 times 2 is 4 square root 3. All right, looks like it's your turn once again. Use your formulas. If you followed your formulas, these should have been straightforward problems. We wanted to find the values of x and y. The first thing I did was I went over and labeled all of the parts of my triangle. I knew I had a right triangle with an altitude to the hypotenuse, which means I've got altitude, leg 1, segment 2, and hypotenuse. And we could certainly put leg 2 in there, just in case we needed it. We label everything. And so I started with x. X is leg 1. That means I use leg 1 as my means. Hypotenuse over leg 1 equals leg 1 over segment 1. So throw it in. Cross multiply. X squared is 36, which is a perfect square. X equals 6. So that's handy. Now, how do I find y? Y is my altitude. Well, we have a formula for that. Altitude is your means. Segment 1 and segment 2 are your extremes. Plug in my numbers. Y squared equals 20. So y is the square root of 20. 20 factors into 4 and 5. So the square root of 4 times the square root of 5. Square root of 5 can't be reduced anymore. Can't be factored anymore. So square root of 4 is 2 times the square root of 5. So I put it in simplest radical form. I believe you can do those. You are just going to have to be careful. And think about what you're doing. Label everything you know. Write your formula and substitute in. I know I've said that a million times, but it's worth saying again.